organisers for putting on such a great programme and for giving me the opportunity to speak here. I'm going to kind of change tack. Is that okay? No? Yeah? No? Yeah? No? 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 Yep. Okay. So, I'm very interested in scalable statistical inference, and what I want to try and convince you is that there are some really interesting techniques that have been developed in recent years, and I guess in recent years, maybe the last 20 years, in theoretical computing science that I believe could help considerably in our kind of thinking about statistics, about inference, about algorithms, about computation, and about doing modeling and computation in a more scalable way. Okay, so as a quick outline, what's wrong with what we're doing now, or what most people are doing now? What is functional programming anyway, and why do some people think it's better than imperative programming? What's category theory? Because the category theory isn't something that was part of my mathematical education. What's it got to do with FP? And how can we use category theory and FP together to make statistical computing more scalable? And what actually does scalable mean anyway? Because that's not really so obvious anyway either. And I'm not going to give definitive answers to any of these questions, but hopefully, you'll get a little bit of insight into how I'm thinking about these problems, and I'll give a few little examples along the way that I hope will be helpful. Okay, so what's the problem? Well, fundamentally, the problem is that all of the programming languages and algorithmic thinking that we use really kind of dates back to the dawn of the computing age, right? If you think about, what computers are like 40 years ago, I know many people in this room weren't even born 40 years ago, but 40 years ago, computers were very primitive things, right? They were really not like computers today. They were incredibly simple, one core. You could run one program on it. You didn't have multi-user operating systems. Typically, you didn't have preemptive multitasking. Usually, right? They were incredibly primitive things, and yet the programming languages we used on those computers are pretty much the programming languages people use today. And if you think about that, that seems kind of crazy. Surely, as hardware has evolved and as our understanding of how programming works has evolved, surely, things should have moved on. And they have moved on, but those developments somehow haven't propagated through to statistics. Okay. No, I don't want more info. Okay, and so that's programming languages, but is it as simple as that? Obviously, there are lots of senior people in this audience. Senior people often don't do much coding. They often have like PhD students and postdocs to do coding for them. So does any of this matter if you're a senior person? Well, actually, I think it does, because I think this old imperative way of thinking about algorithms and computation actually permeates everything, and it permeates how we even think about algorithms. And I think in a very unhelpful way. And I think these two simple examples show this really quite nicely, that here you have two algorithms, and everyone in this room, of course, knows that the one on the left is trivially parallelizable and the one on the right isn't. But actually, if you look at the way you describe these algorithms, typically, this is how people would write down an algorithm. It's really not obvious looking at the algorithm that one of them parallelizes and one doesn't, because they both have this for loop that works through, a loop one at a time, okay, so not in a very parallel or scalable way, and each one has some mutable state, x, that gets threaded through this loop and gets mutated each time through the loop. So it's really not obvious that that one is parallel, right, if you don't already know and you haven't already thought about it. And in particular, it's very hard for compilers to see that that's parallel. And in more complex contexts, it might be really hard for you to see which algorithms are parallel and which aren't. And so this kind of imperative way of thinking about algorithms and computation, I would argue, is really quite unhelpful. And there are different and better ways of thinking about algorithms and computation that I think are more natural, in particularly in the context of scalability. Okay, so Unsurprisingly, computing scientists have been working on programming languages and programming language design for the last 40 years, just as people have been working on computing hardware, just as we've been working on statistical methodology. So we know a lot more now about programming languages and what makes a good programming language. We also know a lot more about how computing hardware has changed, and we've adapted our programming languages to computing hardware. So we actually know a lot, and one of the things that seems to be emerging is that functional programming languages are generally much more scalable, much more modular, and much better suited to modern computing hardware. And by that I might mean a multi-core laptop, I might mean a big server, or I might mean a big cluster in the cloud, okay? So for those kinds of environments, functional languages are just much better suited. They just have the right kinds of abstractions that allow them to more easily exploit that kind of hardware in a natural way. Okay, so where do programming languages live? Well, they kind of live on a little bit of a spectrum, going from kind of very functional to very imperative. And at one end, you've kind of got the so-called church languages based on lambda calculus, and at the other end, you've got the pure imperative languages that are very much inspired by the kind of Turing machine model of computation. Yeah, and what I'm arguing is that there's a general drift in computing science towards the church end of the language spectrum. Okay, these just seem to be much better suited and much more scalable for modern hardware. Okay, so the original lambda calculus wasn't typed, but I would argue that you really need types for scalability, and statically typed languages are now quite popular as well, and they turn out to be very closely related to Cartesian closed categories. Okay, so a simply typed lambda calculus is the canonical example of a Cartesian closed category, so that's the link to category theory. Okay, so what is FP then? Well, in pure FP, all state is immutable. So you can give things names, but you can't then change them. So if you say x is 0, that's fine, x is 0, but you can't then say x is now 1. Okay, that's not allowed, right? Once you've said what x is, you're stuck with that value of x. Well, at least sort of, because if you've got a recursive function where you assign x, you can actually assign x in each stack frame, okay, differently. And so actually using recursion is one of the ways we accomplish what you might think of as general kind of looping tasks in imperative languages, okay? But we usually abstract away the recursion, so you don't normally see it, okay? The other thing we do is we work lots with pure functions, including higher order functions. So higher order functions are functions where you can pass in a function to the function, or maybe get back a function from a function, or maybe both, maybe pass in a function, get back a function. Okay, so higher order functions tend to be used a lot to solve a lot of problems, and again that's very useful and very scalable because it means, for example, it's easy to send computation to your data rather than kind of bringing your data to the computation. Okay, so again this kind of higher order, more abstract way of thinking tends to lend itself to non-trivial data problems. Okay, so why are functional languages more scalable? Well, one is they're just more modular and composable, so it's easy to build big complex algorithms from simple algorithms, but they're particularly good for parallel and distributed computing. So why is that? Well, if you've ever done any parallel programming, you'll know it's really hard, okay? So like 20 years ago, I was writing MPI programs to do parallel MCMC on what would now be like a computer cluster that's less powerful than my phone, but at the time it was like it was a big deal. And it was really hard, and it took ages to debug, and it was really hard to get everything to work well, because you have all kinds of problems when you try and write parallel code that are usually boiled down to problems with shared mutable state. You have some state, and some processor knows about that state, but some other processor doesn't. Two processors trying to write the value at the same time, two processors trying to read a value at the same time. You've got to lock one thread until another thread's finished writing a value. It's just horrible, okay? If you're thinking in this imperative way, you're working in these imperative languages, it's really hard to write parallel code because shared mutable state makes it really difficult. But what I've just said is that in pure functional language, you don't have any mutable state. So you don't have any shared mutable state. And so actually, most of the problems associated with parallel programming just immediately vanish. And not all of them, of course, but a lot of the problems associated with parallel programming just don't happen in FP. If you think in an FP way, you express your algorithms in a functional way, they just naturally parallelize. And and you can't get into all of the problems you get with imperative languages. Okay, so I don't have time to justify the things I'm about to say are desirable for a programming language, but I'm going to claim that you want strong statically typed languages, right? So languages where you declare the types of things. This is an int, this is a double whatever, this is a string. You want it to be compiled because you want it to be efficient, and the combination of static typing and compiling means there are all kinds of errors you can catch at compile time. You want it to be functional for some of the reasons I've hinted at, and you also want it to have a sophisticated type system so that the type system doesn't inhibit you, okay? Well, it turns out that this language, Scala, that I quite like, kind of fits the bill. It ticks most of these boxes. There are relatively few languages that do, but there are some others, and I'll mention some others at the end. So I'm going to use Scala to illustrate these ideas. Nothing about this talk is kind of specific to Scala at all. The ideas are completely generic, but what you need is a sophisticated modern functional language, and I'm just going to use Scala because I think it's a good choice. Okay, so how are we even going to get started with this? Let's try and get started with monadic collections. So what are monadic collections? Well, you have a collection of values, okay? So here we've got a list of values, 1, 3, 5, and 7, right? So that's just some data. And we want to do stuff with data when we're doing statistics. So what might we do to data? Well, we might do some operations on that data. So we might map a function, x goes to 2x, okay? And we'll get back another list of data. And so one of the key ideas here is that we've used a higher order function here, map, okay, which takes a function and applies it to every element of the collection, all right? So we've abstracted away the whole process of iteration here. There is no iteration, there is no looping, there isn't even obviously any recursion, although there is recursion under the hood. We're just doing stuff to a data collection, okay? So we abstract away this need to worry about every single little value that we might want to do something with. We don't do that in a functional language. We just have operations that act on collections of data. And again, that makes our algorithms more scalable, and it means that parallelisation can be exploited under the hood.
Does this mean that after you've done that list, the first list has disappeared?
Nope. So, well, it depends if it's already been bound to something. So if that's bound to something, it will remain there forever and will always be there, and this will be a new list. It won't be, it does not overwrite the existing list, right? Everything's immutable here. So this is a new list that exists completely separately from that list. Another important operation is flat map. So what's flat map? Well, flat map just is a version of map that maps and then flattens. So if you've got a function that maps to a list and you map that over a list, obviously the obvious thing you would get back would be a list of lists. But if you flatten that down to a single list, then that's a flat map operation, okay? So if you have a map operation, we call it a functor. If we have a flat map operation, we call it a monad. The reasons will become clear soon, okay? But we just do, and these are two very important operations for doing stuff with data. Okay, so what's so special about this flat map? Why do we, isn't that a weird thing to have a map and then a flattening and then to give it a name? Why is it so important? Well, it turns out to be important because it allows us to compose functions in context. So if we've got regular functions, you know, one that goes from S to T, one that goes from T to U, one that goes from U to V, we can just compose them together, okay, to get a function from S to V. But if we've got two functions that have a context associated with them, say they're generating a list or they're just encapsulating something in some other context, okay, we've got a function S goes to M of T and a function G goes from T to M of U. They don't compose, right, because the types don't line up, okay? We can't apply the function T because we don't have a T, we only have an M of T, all right? But what flat map does is flat map allows you to do the composition, okay? So people talk about monadic composition because we're able to stitch together two functions that carry some context in a canonical way, okay? And again, this crops up an awful lot in all kinds of programming, not just messing around with data, in all kinds of other contexts as well, but we'll see it cropping up in, you know, statistical kind of data processing in a short while. And it's such a common thing that actually most functional languages have special notation for it. In Scala, it's actually called for, which is possibly confusing because it's not a for loop in the usual sense. but it sort of looks like a for loop, okay? We take something from this collection, something from that collection, something from that collection, and then yield the values, okay? So it sort of looks like a nested for loop, and that's why it's called that. It's called do in Haskell, but this isn't a for loop. It's just sugar for this chaining together of functions in a monadic context. Okay, so before we kind of dive into some more examples, what other kinds of monads are there, right? There aren't just collections of data. There are all kinds of monads that crop up in all kinds of different contexts. So kind of an interesting one for statisticians is the probability monad. So probability is also a monad, okay? And so the idea is that the monad will capture a distribution over a particular type. So if t here is an integer, a rand t would be a random integer, okay? It wouldn't be a draw from the distribution, it would be the distribution itself, okay? Or if t was a double, it'd be a random double, a random quantity. And these are often used in functional languages to avoid issues with kind of random number state and mutating random number state. We're going to kind of gloss over those issues a little bit in this talk, but it's potentially an issue, and this is potentially a nice way to deal with it. But the point is that map can be used to transform one random quantity into another. Okay, we've got a random quantity, we apply a function to it, it gives us another random quantity. Okay, and flat map is used to chain together two stochastic functions to create joint or marginal random variables. Okay, so this notion of map and flat map is again chaining together functions in context. Okay, and so this can be used to kind of propagate uncertainty through a computational pipeline. Okay, and essentially all probabilistic programming languages are just monads, okay? So we'll come back to this at the end if I have time, because it's helpful to know a little bit more about monads before we get into that. But essentially all probabilistic programming languages are just probability monads, and that's kind of potentially a useful insight as well. Okay, but what about parallelism? So we've got our little collection. So here we've got a vector consisting of numbers 3, 5, and 7. We're going to map this function on it. We get back another vector. Of course, we know that because this is a pure function applied to this collection, each one of these elements can be processed independently. So there's no reason why this map operation can't proceed in parallel, okay? And so it can. And in a language like Scala, you can convert a regular collection to a parallel collection just by putting .par after it. And so if we do the map back, we get a par vector. But the point is that this is now being carried out on all available cores, right? You haven't had to do anything. You haven't had to write any parallel code. You just said, okay, if I've got a parallel collection and I map it, I want that to happen in parallel, okay? We can also do reductions, so-called folds. So if we want to sum all of the elements, well, we can use the reduce combinator with a plus function, and that will give us back the sum. In complete generality, folds like this don't parallelize, but many do, and so in particular this one does. This one does because actually the type is a monoid, okay? So a monoid is a semigroup with an identity, or if you prefer, a group without an inverse, okay? So we've got a binary relation which is closed and associative and an identity. And the point is that because the operation is associative, you can combine the numbers in any order you like. And because you can combine them in any order you like, you can actually map them onto a binary tree and compute the sum using binary tree reduction. Okay? So if you've got a reduction on a monoid, then that can proceed in parallel. Okay? So a map is essentially order 1 on infinite parallel hardware. So by infinite parallel hardware, I just mean you've got as many processors as data points. Obviously in practice you won't, but it's a useful kind of asymptotic limit to think about. And so reductions will go from order n to order log n, right? Because that's the height of your binary tree. Okay? So maps go to order 1 on parallel hardware. Folds, scans, and reduction operations go to order log n on parallel hardware. And there's no reason why your code should care about parallelism at all. Okay? And you've almost certainly heard of map reduce. Well, that's just a pattern where you kind of do a map on your data, okay? And then you do a reduce on the result, okay? So that's all map reduce is. It's just two basic functional combinators on a data collection. You can sometimes merge them together, and that sometimes goes by the name of fold map, and that can be useful to avoid creating intermediate collections. Okay, so I want one example before we kind of get into the details of what category theory really is and what a monad really is. just to kind of illustrate the idea of how we can write algorithms that are completely parallelism agnostic. So maybe you want to compute a likelihood, and maybe that likelihood is a product over a huge data set, okay? So what we can do is we can define the likelihood for a particular observation. Doesn't matter what that is. It might be a Gaussian likelihood or t or whatever. It doesn't matter, okay? So we've got a function that isn't parallel at all. It's just a serial function that evaluates the likelihood given a parameter and an observation. And then our log likelihood function is going to just be the function that takes the data, maps our likelihood function, and then reduces by summing, okay, assuming we get back a log likelihood, yeah? And so if I pass in a serial collection, this function will evaluate serially on a single core. If I pass in a parallel collection, it will operate in parallel on all available cores, but I don't change my code. So I write this function log likelihood once, okay, and it will evaluate serially. If it's serial, it will evaluate in parallel. If it's parallel, I don't care. I don't have to change my algorithm when I want it to run in parallel. I don't have to change my algorithm when I want it to run on a big cluster in the cloud. I use exactly the same code, exactly the same algorithm. The context comes from the map and reduce operations that are associated with the type of parallel collection that I'm using. Okay? All right, so that's kind of a little bit of a taste. Now, what is category theory anyway? So category theory is a kind of interesting area of mathematics that I certainly don't have time to get into today. It's basically, it was invented to join together lots of different areas of mathematics and to see the connections between them, okay? So it's very hard to read category theory books because all of the examples involve, you know, incredibly abstract, pure mathematical concepts that I don't understand. So when you don't understand any of the examples, it doesn't really help, okay? But it's been shown to be really, really valuable for understanding these kinds of programming and computational problems. So you just have a set of objects, okay, and you have arrows between the objects, all right? So it sounds a little bit like a graph when you first meet it, but it's not really like a graph because you usually have infinitely many objects, and even when you don't have infinitely many objects, you usually have infinitely many arrows, and you often have uncountably infinitely many arrows. So, you know, intuition coming from graph theory isn't as helpful as you might think. And the real point is that arrows always compose. So if you've got an arrow from X to Y and an arrow from Y to Z, there has to be the composition arrow that goes from X to Z, okay? So you can imagine you can start off with a few arrows and then you add in all of the other arrows that have to be there because the composition has to be there, and that's why you get zillions of arrows very quickly, okay? So the closed under composition, and there always has to be an identity morphism, right? There always has to be an arrow from an object back to itself, okay? And that behaves as an identity. So that's category theory in a slide. So what are some examples? Well, the example I do understand is set. So in the category set, every object is a set, okay? So obviously there are infinitely many of these objects in this category, okay? So every object corresponds to a set, and the arrows between the sets correspond to set functions, okay? So an arrow from X to Y is a function from the set X to the set Y, okay? So that one is okay. And it's a crucial kind of feature of category theory that it's point-free, okay? The objects are atomic. You're not allowed to look inside them. So even though each object is a set and you know that sets contain things, right, you're not allowed to look inside, okay? You can often use the arrows, the morphisms, to probe the internal structure, but you're not allowed to look inside. And that's like what I was saying about data sets. You don't want an algorithm that worries about every little observation that's inside your data set. You want algorithms that operate on data sets as a whole, right? That's how you want to build your algorithms. Okay, so in functional programming, right, the key link-up is that your objects are usually types, like int, double, float, string, whatever, okay? Your objects are types, and your morphisms are functions, okay? And so your category gives you a set of functions and types, okay? And that's a useful way of modeling computation. And so we can then bring insights from category theory right into insights about types and functions and how they compose and how they work and reason together, okay? So for the Haskell programming language, this is usually called Hask, so people often refer to Hask. But in practice, it's very similar to set. If you think about it, a type is kind of like a set. A function from one type to another is kind of like a set function. So you don't go too far wrong thinking about these two things as being the same. And in particular, they're both these Cartesian closed categories. They're both basically models of the type lambda calculus. Okay, so a functor is a mapping from one category to another that preserves some structure. So you first of all have to specify where the objects go. So all your objects in C have to go somewhere in D, okay? And you haven't to mess up the arrows, okay? So if you've got an arrow in C, it has to be mapped to an arrow in D, and the endpoints have to match up, okay? So that's a functor, and so this is actually your mapping. You're taking a mapping in C and you're turning it into a mapping in D, which is inside the functor context, right? So what I said was if you've got a map function defined on a collection, it's a functor. Well, this is the map function, okay? There are some functor laws, they're important, and they just tell you that, well, we'll see, they just are a very basic property you would want to happen. Basically, you want the composed arrow to go to the composition in the destination category, because it would be kind of weird if that didn't happen. But that turns out to be very useful, as we'll see in a second. Okay? So in functional programming, we're nearly always mapping from the set of types back to the set of types, so we're nearly always dealing with ender functors. So when we talk about functors in functional programming, we really just mean the ender functor from Hask to Hask. A natural transformation is a way of mapping between two functors. Okay? So if we've got two different functors from C to D, we can map from one to the other with a natural transformation, provided that it satisfies this naturality law. And again, the details aren't important, but this concept is important in category theory, and it has numerous kind of implications in functional programming for kind of mapping from one parameterized type to another. And then I'm kind of skipping most of a lecture course to get to monads. So a monad is an ender functor on a category that has two particular natural transformations, one that lifts values into the category and another that flattens values out of the category, okay? So we've got a way of injecting values into the category, and we've also got a way of kind of flattening down redundant lists, okay? So remember I said that when you've got a list of lists and you want to flatten that down to a list, that's a flattening operation. You usually accomplish it with flat map. Well, this is the so-called, it's actually called multiplication natural transformation in category theory. And essentially, there are two kind of consistency laws that you require. So one says that the two different ways you could flatten down a list into a list are the same. And the other one says that the two ways you could start with a list, lift it up to be a list of lists, and then flatten it back down again also are the same, okay? And again, those consistency laws are very valuable. In functional programming, we often call monads M. In category theory, they're nearly always called T for triple. And in functional programming, we often talk about three monad laws. That's just because we think about this, this identity law as being two different laws, that's all. Okay, but this notion of chaining together monadic functions is so kind of vitally important and is equally important in category theory that it has a name. Okay, this is a so-called Kleisli category. So for any monad on any category, you can compose together these monadic functions, essentially the analog of our flat map function, and again, they compose together in a consistent way, okay? So in functional programming, people often talk about Kleisli arrows or Kleislis. What they mean is the kind of lifted versions of these functions in context that can then be composed together in a natural way, okay? So that's like the whistle-stop tour of category theory. The details don't matter. What matters is kind of that you see that there is this correspondence between this kind of slightly abstract area of pure mathematics and the practical things people do to solve real computational problems in functional programming. Okay, so a really neat library that was originally came out of Berkeley's AMP lab, I think, Apache Spark. It's basically just a Scala library for big data analytics, and it runs on big clusters in the cloud. Well, actually, you can run it on your laptop, right? There's no problem running on your laptop, but it's really meant for processing internet scale data on big computer clusters, usually in the cloud, right? So on Amazon, you can just say, okay, I want to spin up a Spark cluster with 100 nodes, okay? And you get a Spark cluster with 100 nodes, and then you can process your data on this 100-node cluster, yeah? So that's what it's for. But how does it work, and why does it work? It works because all it is a lazy distributed parallel monadic collection, okay? So it basically just gives you an abstraction for your data set that is exactly the same as those other collection abstractions that we've seen, and so we can operate on this huge data set in the cloud in exactly the same way as we operate on a list with 5 elements on our laptop. Okay, it's exactly the same. Yeah, we get our RDD, it's just a handle to that cluster or a data set on the cluster, and we can use things like map and flat map and reduce, etc., in order to process that data. And again, what that means is we can write an algorithm that works for a little data set on our laptop, and then we can deploy that algorithm, that same algorithm, without changing any code necessarily, on a huge cluster in the cloud to process terabytes of data, petabytes potentially, with exactly the same code, exactly the same algorithm you've just written on your laptop, without having to worry about parallelization and distribution at all. Okay, and there are some cool things about these RDDs that are a little bit different from regular collections. So in particular, they have lazy semantics, and that turns out to be useful for avoiding data shuffling. So the thing that really kills you with distributed data processing is data shuffling, right? That you really don't want to shuffle data. So that is move data from one processor to another, or one machine to another over the network, right? That really kills you. So you want to do everything you can to optimize your computation so as not to shuffle data. So for example, we suppose we've got a data set RDD, we want to map a function f, then to the result of that we want to map another function g, and then to the result of that we want to reduce it with some reduction operation. Okay, that's a standard kind of computational pipeline. Okay, well you can do that, but actually you might note that we could rewrite that as let's take RDD and map it with a composition of g and f. Okay, with g after f. Okay, we can do that. Why can we do that? We can do that by that second functor law that I said was important, right? So remember, map is our kind of functor combinator, and we can use our second functor law to fuse those two maps together into a single map that avoids creating an intermediate collection. So that's going to be much faster and more efficient, and we know that we're allowed to do it because we know we've got a functor, and the functor law says that we're allowed to do that. Okay, so these laws from category theory that I just glossed over actually very often correspond to optimizations that can automatically be applied to code, and a system like Spark can even analyze your computational pipeline for you and apply these kinds of optimizations for you in order to minimize the amount of data shuffle that happens on these huge data sets. Okay, so yeah, so Spark's fantastic for big data, but actually with a little bit of thought, it's pretty clear that you can exploit it for big computation as well. Even if you don't have huge amounts of data, if you have a big model, or you have a particle filter with a large number of particles, or a particle filter where simulating from the forward model associated with each particle is very slow, you can still exploit this. You know, we can make the particles our data, okay? And then we can spread the particles across the cluster, and we can run our particle filter in parallel on a big cluster in the cloud, okay? So it's not just about big data, it's about big models and big computation as well. Okay, so I'm kind of rapidly running out of time. So we need a way of kind of describing these important objects that we work with, the important classes of things that we work with, okay? Classes of types, you could say, or type classes. So something like a monoid, okay, that's kind of simple, but that's an example of a class of types, right? There isn't just one monoid, okay? There are lots of monoids, but all monoids belong to the monoid type class, okay? Similarly, there are lots of functors and lots of monads, and we want a way of describing generically, look, this thing belongs to this functor type class. So there is a way of doing this in advanced FP languages called type classes. It's not the same as classes in OO languages, but it's sort of a little bit similar, only better. Okay, so to do this, you actually need this sophisticated type system, so you need to be able to have types with parameters, which are themselves types with parameters, which are themselves types with parameters, these so-called higher kind of types. And again, very, very few languages support higher kind of types, but there are a few, and I'll give you a few at the end. So the monoid type class just has a combine operation and an identity operation. The functor type class just needs to have a map. The monad type class needs to have this unit, this way of injecting values into the monad, and it needs to have this flat map, okay? But we can define our own type classes, and so for doing statistics, we might want a generic collection type class, okay? So we might want to have a collection and where we don't care whether it's serial or parallel or a Spark RDD running on a huge cluster in the cloud, we just want to do stuff, okay? So our generic collection, well, we want it to be monadic, so we want it to have a map and a flat map, but we want to have some other things as well. We want it to have a flat map, a reduce, a zip, a length, maybe one or two other things as well, like a scan, a fold left, etc. So we want it to have a few things that we can do with it, but then we want to write our algorithms so it only uses these basic combinators, okay? So then our code is completely generic and it will work for anything that belongs to this generic type class, okay? So for example, ABC, right? Lots of people do ABC. How do you do simple rejection ABC? Well, you set up your model so that you have a sample from your prior in one of these generic collections. Then you need some other features. You need some data. You need your simulation model that maps from parameters to data. You need summary statistics. That's a function that maps from data to your summary statistics. You need a distance function that maps from a pair of summary statistics to a number. And then what's ABC? Well, ABC just says, okay, we compute the real summary statistics, and then for our sample from the prior, we map the composition of the summary statistics with a simulation model, and then filter the results, keeping only the ones that satisfy this predicate. And notice here we've used map fusion to avoid constructing a collection of synthetic data sets, because your synthetic data sets might be huge, whereas your summary statistics might be small. So you don't want to create a huge collection of data sets. You only want the collection of summary statistics. Okay, so that's ABC in kind of one line of code. What about particle filtering? Okay, so a simple bootstrap particle filter. Let's think about one observation, right? Processing one observation. So we have a prior at time t minus, posterior at time t minus 1. We have our observation at time t. We want to combine them to get a particle distribution at time t. How do we do that? Well, we take our particles, we map them with a forward model. We then map the proposed value, the proposed particles with the likelihood function. We then might want to do the log sum x trick. The details don't matter. If you know it, you know it. If you don't, you don't. And then we probably want to resample to get an equally weighted set of particles again. Okay? And then we might want to keep track of the marginal log likelihood if we're going to embed this into a PMCMC algorithm. Okay? So we can do that, but we're just using these combinators, so we don't care, right? If we pass in a serial collection, it'll happen serially. If we pass in a parallel collection, it will happen in parallel. Okay? Similarly, resampling. How do we do resampling? We do that in parallel as well. It's easiest with Poisson resampling. We just use our friend flat map here to duplicate the particles, okay? And this is a very useful way to duplicate the particles because it's got good data locality, okay? So if you're doing this on a distributed collection on a cluster, flat map has good data locality properties. Okay, it will generally keep the descendants with the original ones. It'll have to rebalance itself at some point, but that's not your problem. That's the problem of the parallel collection you're using. Okay, so you can do Poisson resampling. Poisson resampling isn't the best on long time series. Multinomial resampling is kind of interesting. So that's easy to express with simple combinators in a serial way using something called fold left. You can do it in parallel as well, but it's a little bit more involved. Okay, it needs a kind of a down sweep on a binary tree. A little bit involved, but systematic resampling is usually better anyway, and that's really easy to express with these combinators. Again, you need the cumulative weights, but the cumulative weights is a scan, and if you've got a parallel collection, a scan can be computed in parallel using what's normally known as a parallel prefix scan. Okay, it's just an upsweep on a binary tree. Okay, so we can do that in parallel. So none of these operations are order n operations. Okay, we can do resampling for our particle filter without any order n operations. Then we want to fold, okay, to run our particle filter on a sequence of observations. So streaming data algorithms have been mentioned a couple of times. So a streaming data algorithm is just an algorithm that can be represented as a fold left. Yeah, you start with your first value of the stream, you do something, you combine it with an accumulator, you pass the accumulator on to the next observation, you consume the next observation. That's what this fold left combinator does. Okay, so that's a fundamentally serial algorithm. Okay, you process one observation at a time, but the updater here, our particle filter, is parallel. Okay, so that's kind of an example of a recursion scheme, and I'm really running out of time now. So these recursion schemes have There are lots of different recursion schemes for doing data processing. They all have fancy names from category theory. So a fold is actually a special case of a catamorphism. An unfold, where you generate a sequence of values, like in an MCMC algorithm, that's a special case of an anamorphism. If you imagine doing an MCMC algorithm where you generate the values, but you don't keep all of the values that you generate them, you kind of consume them one at a time to compute summary statistics like posterior means or whatever as you generate them. Okay, that's a refold, what we call a refold in functional programming. It's called a hylomorphism in category theory. There's lots of stuff I'm glossing over here that I don't have time to go into, and some of it I barely understand myself. So that's kind of scalable computation. So I think we kind of solved a lot of the problems of kind of scalable computation using these functional ideas, these kind of abstractions that sit just above the details of how parallel collections are implemented. But what about modeling itself, right? We want modeling to be scalable as well. And as I hinted at the beginning, a lot of kind of scalable modeling, generic modeling, is done with probabilistic programming languages, okay? So things like Bugs, JAG, Stan, etc., where you build up a model from small, simple components. So again, this is composing small things together to make bigger things. It's exactly what functional programming languages are good at, but in particular, when we're doing this with probability distributions, we're doing it with the rand monad, okay? So, as I suggested at the start, we've got this notion of you take a value and it goes to a random number. We can use flat map to combine and chain random distributions together to create basically conditional distributions, okay? So we take a marginal and a conditional, and we stitch them together with flat map to get a joint, okay? And if we look at what that looks like with our kind of for notation, okay, it looks exactly like a probabilistic programming language. This looks exactly like the kind of thing you'd write in Bugs or JAGs or something like that, okay? But this isn't a specially written probabilistic programming language. This is just off-the-shelf Scala code, because actually a probabilistic program is just a monad, okay? So it is just composition in the rand monad, okay? And there's something called free monads that are useful. So here's some MCMC algorithms. We just iterate, okay? We've got a way from going from one state to a new state. We just iterate it. That's an unfold. I've kind of glossed over issues to do with random number streams and whether we're being pure or not pure, and are we mutating a random number state in the background or not. But it's easy enough to kind of map from one to the other and kind of defer our kind of impurity as far as possible. But at the end of the day, we are going to need our random numbers at some point. Okay, so at some point we've just got to execute our probabilistic program and get our stochastic results. Okay, so smart people have been thinking about kind of good models of computation for decades. I personally think that these functional programming languages are a good way of kind of expressing these algorithms. And I think it narrows the gap between theory and implementation. I think it's much better to go from maths to maybe a category theory representation of the maths to a functional language implementation than via imperative algorithms and imperative programming language. So I think that the gap there is much bigger, and there are many more kind of ways to kind of trip yourself up when you go that way. Okay, so yeah, so I like this language Scala. I've used that to illustrate, but there are other interesting languages as well. Haskell's a great language, though it's now showing its age. Idris is a very cool language. Things like Frege and Eta are derivatives of Haskell. They're all cool languages, but of course they're all languages that statisticians by and large don't use. Okay, so that's kind of a shame. Okay, so I've not archived much on this sort of stuff, though I have kind of blogged about this kind of thing occasionally. So I've just left a few references here, mainly kind of classic papers in the field, but also a few more recent perspectives. That's all. Thanks very much.
So it's very interesting and it's very exciting. Have you ever found situations when sort of the fact that a lot of the difficult things have been abstracted away actually hinders something? It kind of hinders you from having the control which could improve performance in some situations.
Well, the short answer is yes. So it's kind of interesting that algorithms that are for example, difficult to parallelize. Not every algorithm is difficult to parallelize, right? So if you're struggling kind of thinking about how can I kind of express this algorithm in a functional way, sometimes you're struggling to express it in a functional way just because it's fundamentally difficult to parallelize. So usually you either kind of, it becomes clear and you express it in a functional way and suddenly it parallelizes and everything's great, or you realize why actually it's never going to parallelize and you just have to write it as a fold left, and you know that's just the way it is. Yeah. So the short answer is yes, but you know it's mainly just a different way of thinking, and when you get tuned into that different way of thinking, you kind of understand that with great power comes great responsibility, and that ability to kind of mess with stuff and mutate stuff actually is a rope around your neck, really.
Any other questions? Let's thank our speaker.